So now that we know a lot of concepts about binary operations, the different laws that can be applied to binary operations, that is the commutative law, the associative law, and the distributive law. We know what we mean by the identity element and the inverse element. And in my last video, I have also talked about the composition table, and we have learned two new operations. Of course, if you had learned them before, that's not new for you, but we have discussed about the addition modulo n operator and the multiplicative modulo n operator. So now that we have this knowledge domain, we are ready to work out certain examples of the binary operations. So let's first look at the first sum that we have here. So the first sum says, prove that union and intersection of two subsets of a non-empty set S are binary operations on PS. Here PS essentially refers to the power set of S, and as we have defined, power set of a set S is defined as the set of all the subsets of S. So if we have a set S, there are certain subsets that we can have that belongs to S. So we can have, in fact, null set is also a subset of S, and set S is also a subset of S. So the set of all these subsets of S combined forms the power set of S. So that's a definition out there for you. So that's the power set. What we need to prove is, we need to prove that union of two subsets of a non-empty set S. So if we are talking about S, then the operation will be binary operation on power set. So that is what we need to see. In this sum, I have discussed about the union operation, and what I want you to do is, I want you to try out the intersection operation. Needless to say, in my future videos, I will be referring back, I will be falling back to this video such that I can explain the intersection part of this video, but I want you to try it out once for yourself as well. So to find out how you do it, look at this union part of the sum and just try to, collaborate or correlate and continue forward the procedure. It's almost the same procedure, just as the slight concept difference between union and intersection, and you'll be able to find out. It's not that difficult. So what we first do is, we first start with whatever has been given to us. So prove that union of two subsets. So we need to consider two subsets A and B, which are the subsets of S. So since it says two subsets of a non-empty set S, we consider two subsets of the non-empty set S. So the two subsets under consideration are A and B. And as I had mentioned before, since power set of S, that is PS, is essentially the set of all subsets of S, if A and B belong to S, that is, let's take a different color. So if I have, let's say this blue color is essentially A, and let's say this pink color with a thick outline, let's say this is B. So A and B are subsets of S. If A and B are subsets of S, it means A and B are also elements of PS. So if A and B are, again, note this notation, A and B are subsets of S. But all the subsets of S form elements of PS. So there's a difference between whose element is who and whose subset is who. So A and B are subsets of S, and since they are subsets of S, they are elements of PS. So that's the first trick of the sum. Now, if A and B are subsets of S, by definition of union, we mean that essentially if A and B have certain elements, A union B considers all the elements of A and B taken together. So let's turn back to our example. So let's say if this is A, and if this is B, then this entire portion is A union B. So if A and B are inside the set S, then A union B will also be inside the set S. So that means if A and B are subsets of S, that means A union B is also a subset of S. Again, using the same logic that I used here, that is A and B being subsets of S implies that A and B are elements of PS. I can do the same thing here, and I can say that if A union B is a subset of S, it means A union B is also a it's also an element of PS. So again, as you can see, A and B is a subset of S. A union B, sorry, is a subset of S, but A union B is an element of PS. So now, if we take equation 1, that's too thick of a line. So if we take equation 1 And if we take equation 2 together, let's look at these two equations, moving everything else aside. So we have A and B are two elements of PS, and when we operate on them, we get A union B, which is also a subset of PS. So going back to the definition of binary operation, we defined it as a function which maps every element of the range to the S cross S elements. So this essentially means that union is a binary operation on PS. So that is what I have said. Combining 1 and 2, if A and B belonging to PS implies A union B also belongs to PS, that means union is an operation. Union is a binary operation on PS. So that is how I say that A union B is a binary operation on PS. The intersection just follows the reverse order. What you'll be doing is you will say A and B are subsets of S. If A and B are subsets of S, then we can of course say A and B are elements of PS. So up until this level, the sum remains the same. After this, you'll say, so let's take a different color. If A and B are elements of S, then we define A intersection B as the elements which are common to both A and B. So if A and B are belonging to or are subsets of S, then A intersection B will by definition also be a subset of S. And going by that procedure, A intersection B will also be an element of PS. So A intersection B will be a subset of S, and A intersection B will be an element of PS. So again, you will combine equation 1 and equation 2, you will get A and B being subsets or elements of PS. A intersection B is also an element of PS. So you'll be able to conclude that intersection is a binary operation on PS. So there I just explained the part that you were supposed to do on yourself. So, well, it's easy for you. The next sum that we'll be taking into account is a very interesting sum that I find is, if S be a set of n elements, how many different binary operations can be defined on S? So we look at it at a pictorial way. So let's read the sum again. If S be a set of n elements. So up until now we know that the set S has n elements. So let us say that the elements of S are respectively E1, E2, some EI up and EN. So that is the number of elements in the set S is n. So that is how I write this. This is the notation. Number of elements in a particular set is the number. So that is the notation. So let me just block that for you. So that's a notation there. How many different binary operations can be defined on S? So we'll take it step by step. The first step is, as I have explained the situation at hand. So I have mentioned this before. Whenever you start a sum, you should first start with whatever has been given. And there are two ways. Either you keep on analyzing what has been given, and if you're good at it, you will end up at the point where you need to arrive. Or the other way is to you back calculate. You start back calculating from the end, and you try to arrive at what is given. So if it's a two-way traffic, then since you have back calculated from the solution to the given, it means you will be able to track your way back from the given to the solution. So that's another way of doing the sum. In this step, in this sum, essentially we'll be doing it the ordinary way. So we'll be moving from the given portion, and we'll be trying to arrive at the solution. So as I've mentioned before, I have defined I have essentially named the n elements of the set S under consideration. What I'll be doing next is, as I had defined before, binary operation is a mapping which maps different elements of S cross S to different elements of S. Essentially, it's a correspondence, a relationship which connects each element of S to a particular pre-image on S cross S. So what we'll do is we'll start with S cross S, that is we'll start with the origin of the mapping or the origin of the binary operation itself. And what we'll be doing is we'll try to find out how many different combinations or how many different ordered pairs of elements we can find in S cross S. So moving on to the definition of ordered pair, what I mean here is an ordered pair essentially is a combination or an ordered combination, to be very precise, of elements. So let's say you have a set of elements 1, 2, 3, 4, and you have another set of elements A, B, C, D. So what you do is you take one element from the first set and you take another element from the second set, and you put them together and you keep an ordered list. So 1A, 1B, 1C, 1D, 2A, 2B, 2C, 2D, and you move on in this way. Why it's called ordered pair is, when I'm saying S cross S here, since I'm repeating the same set, it doesn't matter. But let's say you had a set N, which essentially here represents numbers. So you had the set N, which has 1, 2, 3, 4, and you have the set L, say, which stands for letters. So N has the elements 1, 2, 3, 4, and L has let me just write that down. So let's say we have a set N which has 1, 2, 3, 4, and we have the set L which has A, B, C, D. So N cross L will have the elements 1A, 1B, 1C, 1D, 2A, 2B, 2C, 2D, so on and so forth. But the L cross N set will have different elements. It won't have the same elements since the order has been changed. In case of L cross N, we'll have the elements as A1, A2, A3, A4, B1, B2, B3, B4, so on and so forth. So as you can see here, the order is of prime importance in case of this combination of these two sets. So that is why it's called an ordered pair. The order is of prime importance here. Since in this case we have considered S cross S here, the order essentially doesn't matter, but as we had discussed about commutative law, in certain cases we need to consider the order that they are in. So that is what we essentially mean by the ordered pair. Now coming back to the sum, if I start again, so for every EI I can return it back to E1, E2, E3, E4 up to En. So the elements will be E1, 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 E2, E1, EI, then EI, E1, En. So there will be n such numbers here. For every E1 I'll get n because there are n elements of S. So since I had 4 elements here and I had 4 elements here, so that was 4 times 4. So it's E1, 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 E2, E1, EI, E1, En, and we have n elements. Taking the next element, so we are done with this element. Next we take this element and the entire set. So it's E2, E1, E2, 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 EI, E2, En. So the second element is done. Moving on, we go on to the ith element. So the ith element will again connect with all the elements each once. So we have EJ, EI, that should be EI. So, or you can take, in fact, you can take G as well, so EJ as well. So let's say we had another element here, EJ. So you might not have the same EI. You can have had another some EK or EJ as well. So EJ also connects to each of the elements of S. So we have EJ E1, EJ E2, EJ EI. So here you can see this might not be the same element. These two might be different elements since we have here E2 E1, EJ E2. So they need not necessarily be the same numbers or the same suffixes. So we can have EJ EI. Since the other reason why I had taken this is to show that this number need not be the same, because this column is essentially the ith column and this column is the jth, this row is the jth row. So for every such row we have n elements taken under consideration, and even if we look at the columns, so it's E1 E1, E2 E1, EJ E1, En E1. So even every column has n elements. So we have n elements along every row and we have n elements across every column. So there are a total of n cross n, which is n square elements in S cross S. So that is, sorry. So there's a total of n cross n elements in this S cross S subset, or the S cross S set essentially. So we have n of S cross S is n square. That is, there are n square. The number of elements of S cross S essentially is n square. So that follows the same notation that I used before. So let me just block this as well, so that you can relate that these two essentially denote the same meaning, just for different sets. So n, the number of elements in S is n, and the number of elements in S cross S is n square. So that's an important or integral part of the sum done. The next part is the most, how should I say, the conceptual way of the sum. Conceptual part of the sum essentially. So what we do is, here we have listed the elements in a short form essentially. We have listed the elements of S cross S and we have listed the elements of S. So as I had mentioned before, there are n square elements here in the S cross S set, and there are n elements here in the S subset. So every element in S cross S can be connected to n of these elements in the set S. So every element has n ways of mapping. There are number of mappings for S. Essentially, for every element, there are n ways in which it can be mapped to the element S. So for n square elements, so this has n ways. There must be an element here which has n ways of being mapped to the set S. This last element en cross en essentially also has n ways in which we can map it to the set S. So for every element in S cross S, there are n ways in which it can be mapped to S. So for all these n squared, we'll have n times n times n times n, and this will repeat n squared times, because there are n squared elements in S cross S. For each of these n cross n elements, we have n operations on this side, so it will be n squared times n, and if we multiply them, it essentially is n to the power n square. So essentially, the sum boils down to the statement or fact is that if S be a set of n elements, then the number of then there can essentially be n to the power n square. So let me just block it again for you. So yeah. So essentially, if there are n elements in a set S, then there are n to the power n square ways in which the binary operation can connect elements of S cross S to S. So that's a fact essentially, and it's a very important fact in binary operation theory.